Okay, good morning. In case you needed help on the 141 extra practice worksheet, that's what I'm going to walk you through. I also will just post the PDF to my key if you don't want to listen to the video or the explanation as well. Okay, cool, here we go. First of this, I am a knucklehead in that a lot of this, or the front side of this, is just like the notes. I posted the notes, I think on Saturday morning. They're in Wednesday, they're in Friday of the calendar, so you can see the second part of the notes and how to do this front side of the homework. If you already did this in your notes, then you don't have to do it again on the homework. So let's go to page 2, shall we? All right, so here we go. The general formula that you want to get into your head is this. All right. A Maclaurin series is a Taylor with a center of 0. Sorry about that, my phone's blowing up. All right, writing a Taylor problems. Wow, nice subject-verb agreement there. Sorry about that. Writing Taylor problems. Oh, sorry. So the way I understood this is an outline form. So here's examples of writing Taylor problems. All right, so if they give you facts about the function, the derivative, the second derivative, etc., then you should be able to write a Taylor. The Taylor here then, using the same idea here, is h at 1 plus h prime at 1, x minus 1 to the first over 1 factorial plus h double at 1, x minus 1 to the second over 2 factorial. That is a second degree. Third degree would be one more. My answer to that was D, after simplifying a little bit. All right? 2. Write the Taylor series for natural log about x equal 1. So the idea is I need to find f at 1, f prime at 1, f double at 1, and hopefully along the way I'll start to see a pattern so that I can write the general term a little easier. So gathering the functions in an organized way, I would say f at 1 is natural log of x at 1, which is 0. F prime at 1 is 1 over x at 1, which is 1. F double at 1 is negative 1 x to the negative 2 at 1, which is negative 1. F triple is positive 2 x to the negative 3 at 1, which is 2. Now I'm starting to see that exponent coming down, next greatest exponent factorial thing. So it seems like f triple would be negative 3 factorial, and so on. Now if I throw those in and then simplify, then I'll get something like this. 0 plus 1 times x minus 1 to the first over 1 factorial minus 1 x minus 1 squared over 2 factorial plus 2 x minus 1 cubed over 3 factorial minus 3 factorial x minus 1 to the fourth over 4 factorial. Now, once I get out there, I start to feel confident in seeing what's going to happen. But it did take me a while. You're not going to see a pattern right away. You need to continue out until you see what's going to happen. So it seems like what's going to happen is I have factorials canceling out, and I'll be left with the denominator. So maybe something like positive x minus 1 to the first over 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the fourth over 4. Once I get a feel for the pattern, then I can write the general term. It's x minus 1 to the n over n. It looks like n starts at 1 because I have no term there. So n starts at 1 in my mind, and I would use that if I was writing summation notation. And then the alternating negative. It's negative 1 to the n or to the n plus 1. Well, the first one, when n equals 1, should be positive. And so negative 1 to the n, negative 1 to the first would be negative, so it needs to be n plus 1. That would work and generate the terms. If you were to do this in summation notation, it might look something like that. All right? Next idea in the outline, from a Taylor, finding coefficients of derivatives. I talked about this a little in the notes, which you might want to watch. This is a skill you often need to use in multiple choice. So the thought process goes like this. If they want f doubled, then you need to look at x minus 1 squared. This is the term connected to f doubled. Then you start with the general formula. F double at 1, x minus 1 squared over 2 factorial should be, according to the formula, how you find any Taylor series term. In this case, it's equal to a term of x minus 1 squared over 25. So you find the term you're looking for, set the term they give you to the general formula you would expect, and solve. In this case, x minus 1 squared drops out. If I move the 2 factorial over, I would see that f double at 1 must be 2 over 25. So that answer was C. Do it systematically, not by just guessing and checking. For the next one, which is not really clearly numbered, I, in essence, just said f is cosine, f prime is negative sine, f double is negative cosine, f triple then is positive sine, f pi over 4. Then if you think about the factorial part of it as well, then it would be sine of pi over 4 over 3 factorial. That's what I get an answer of D. All right, so many n's. This is so confusing for students starting out. N could be so many things. For example, what you're putting into the summation formula, you see it in there. It could be the number of the terms you're looking for. It could be the number of terms in the sum. It could be the degree of a polynomial or a Maclaurin series. Wow, so confusing. If we use this idea, then let's talk about how to use our series above, which we said the natural log is equivalent to, at least for some, this minus 1. It was centered around 1, wasn't it? Yes. Okay. Yes. Okay. All right. So if we use it to find an S3 and a T3 estimate of log of 2, how many terms are required? Let's start with log of 2. Log of 2 would mean using the same idea, but instead of using an x, we use a 2. So the series would look something like this. 2 minus 1 to the n over n. Oh shoot, that's nice, because that means log of 2 is roughly equivalent to 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5, and so on. Now, the S3 estimate, to find an S3 and a T3 estimate. S3 is the sum of the first three terms. So 1 minus a half plus a third. So for that I have 5/6. That, by the way, is the same as the T3 estimate because the power starts at 1. That's the same as if I used a third degree Taylor. And you can see that this starts at x minus 1 to the 1 over 1, and then goes x minus 1 squared over 2 plus x minus 1 to the third over 3. So in this case, third degree Taylor and 3 terms to estimate are the same. So my estimate is 5/6, all right? If I said how many terms required to get error below 100th, I'm thinking alternating series error bound. So I would have to look at this pattern and figure out, well, when would I get below 100th? And surely it wouldn't be till I got to the 1 over 101st term. Now, if it starts at 1 and I need 100 and the 101st term is my error bound, then I would need 100 terms to get my error below. So to answer the question, I would say something like 100 terms is the least I would need necessary. And the reason is because this is an alternating series with the limit of the terms is 0 and the terms decrease in absolute value. So it must be the case that the difference between the true infinite sum and 100 terms is less than or equal to the 101st term, which is 1 over 101 with the absolute value, and that is less than 100. So the answer to that is you need 100 terms. All right? These are in your notes. You gradually need to get these into your memory. I think you should have these. Well, I asked for these a couple times. When I asked you these, I want at least the first 3 terms, the general term and the summation notation as it says. So make sure you give me those. You should know if those are correct. If I use the series for sine to estimate the sine of 3, then I would say something like the sine of 3 is, let's start, you probably have the Maclaurin right in front of you, but I'm going to start with the general Maclaurin. Sine is x times x cubed over 3 factorial plus x to the 5th over 5 factorial and so on. So sine of 3 is 3 minus 3 cubed over 3 factorial plus 3 to the 5th over 5 factorial. And generally you would say it is 3 to the 2n plus 1 over 2n plus 1 factorial, which implies n starts at 0. So this is negative 1 to the n to start positive. In summation notation, it would be just like that. N plus 1 over 2n plus 1 factorial. Okay? All right. If I used a 5th degree Maclaurin estimate sine of 3, then it's more like the same through 5th degrees. So it would be the sum of those, which I had was 21 over 40. This didn't go particularly great. I think I wish I would have just said error, but that's all right. The point is still made. So I put this into function 1 and this into function 2. Again, not with 3 in it, but back with x in it. And then I evaluated f1 at 2, f1 at, or f2 at 2, and recorded until I saw something different. So these guys were different in the 100th place. But I think you'll see that because we're centered around 0, my Maclaurin fits well around 0, but the further I get from 0, which is what's happening in this table, the worse and worse the fit. So for example, at 2.3, or 2.5, I'll be different in the tenths by 2 tenths. By 2.9, I'd be different in the tenths by 3 tenths. By 3, by 4 tenths. By 3.1, by 5 tenths. 3.5, I am starting to be different by a whole unit, and something, 1.7, and more. So as we get further and further away from the center of the Maclaurin, our fit of our polynomial to sine is worse and worse. Now that would be problematic if I wanted to estimate something like sine of 4, sine of 3. Show the error in your estimate is less than a half. So that's back to my, I think that's talking about back to the M5 estimate. First meet the conditions. The series sine of 3 is approximately 3 minus 3 cubed over 3 factorial plus 3 to the 5th over 5 factorial is an alternating series. The limit of the terms is eventually 0, and the terms start to decrease after a certain point. This is 27 over 6. This is what, 81, 243 over 120. So they are, this is roughly 2-ish, that's 4-ish. They are starting to decrease after n equals 2. That's true. So it is true that the difference between the two true infinite sums, sine of 3, and my estimate of 21/40, which is equivalent to infinite sum minus 3 terms, is less than or equal to the fourth term, which the fourth term in the pattern would be 3 to the 7th over 3 factorial, which is still probably a good chunk of error. All right? All right. Sorry. Let's say then how we wanted to get less error. Well, there are two ways to get less error. I can choose a center closer to what I want to estimate, and that would help. Or I could use more terms. Instead of stopping at the 5th degree, I could keep going and I would get a better estimate that way. All right. If I use pi as the center to find the Taylor series, then I'm saying the function is sine of x, the center is now pi. So my Taylor then, with different derivatives, was negative 1 x minus pi to the first plus 1 x minus pi cubed over 3 factorial minus 1 x minus pi to the 5th over 5 factorial. Generally speaking, x minus pi to the odd over odd. And assuming that n started at 0, then I would need negative 1 to the n plus 1 to start negative. All right, and again, you could write the summation notation with n starting at 0. So if I use tried to estimate sine of 3 using 5th degree again, but using my new series, sine of 3 could be approximated by negative 3 minus pi, which, think about that, that's really small. 3 minus pi is about 0.14, plus 3 minus pi cubed, about 0.14 cubed, really small, minus 3 minus pi to the 5th over 5 factorial. These should be small. Sine of 3 is close to sine of pi, and therefore I imagine it would be very close to 0. there's my estimate. I just left it like that. Oh, actually, I did calculate. It's about 0.14112. All right. Now, I placed, again, I put F sine in F1 and my Taylor in F2, and now try to see how different they. I just lost my microphone. Um, so I again calculated both at these values and compared and went out until I found a different place. So for example, these were the same until the tens, hundreds, thousands, 10,000s. And because it's centered at 3, or pi actually, as I got closer and closer to pi, the difference between the two got even smaller and smaller. So for example, here is 0.59847, whereas this is 0.59848. Now we're accurate through the 10,000th place, and they're different by 100,000. I continued that on here. That's your job. You should be able to do that. And yes, I expect you to do that. Yes, you have to do that. Hopefully you'll find that as you get closer and closer to 3.1, they get all but the same. They're only really the same at pi, but 3.1 is doggone close to pi. All right, and as far as an error bound for my new estimate up here in part B, if I were to look at these terms here, they definitely are alternating. The series here in B alternates. Terms are definitely going to 0 and very fast, and they are decreasing in value right away. So it must be true that the difference between the true value of sine of 3 and my estimate of 0.14112, which I guess I could say is the infinite sum minus my 3-term partial, or I could call it M5 at 3, is less than or equal to A4, and that would be 3 minus pi to the 7th. That's like 0.1 to the 7th power, 100 million, or 10 million-ish, over 7 factorial, even smaller. That's all but no error. That's tiny. All right. So the point is, by choosing a different center, you decrease the error considerably, and you get a far better estimate. All righty. Cosine of 32 degrees. First, let's get these in radians. 32 degrees is 32 pi over 180. 30 degrees, obviously, is pi over 6, or if you like, 30 pi over 180. Okie doke. So, finding all the function values and the derivative values at pi over 6, not at 32 degrees, which you don't know. You find them at a good place, like 30 degrees, and then you put 32 degrees into your Taylor. So my Taylor looks like this. That's cosine of 30 degrees. And then there is f prime, negative 1/2 is f prime at 30 degrees, minus root 3 over 2, x minus pi over 6 squared over 2 factorial. It didn't say how many terms, so I'm going to go through third degree. It's hard to write a general term to this. The pattern is kind of wacky, so we're just going to go through third term, or third degree. Sorry, I should have specified that in the question. All right, there's your third degree Taylor. So if I then use that to estimate what's cosine of 32 degrees, it could be approximated by the Taylor at 32 degrees, which is 32 pi over 180. So that's root 3 over 2 minus 1/2 of 32 pi over 180 minus pi over 6. Well, that's 32 pi over 180 minus pi over, or 30 pi over 180. So that amounts to 2 pi over 180 or pi over 90. Minus root 3 over 2, 32 pi over 180 minus pi over 6. Again, that would be like 2 pi over, or pi over 90 squared. And then finally, that. Yeah? Okie doke. So again, if you really wanted, if this were a multiple choice, you might see this as a possible solution. All right. Could we use alternating series error bound here? The short answer is no, it's not alternating. You would need some other kind of error bound, and that's Lagrange error bound. All right. Once again, trying to get Maclaurin in here. I'm trying to get you to write these a few times so we can accelerate the process of getting those in your brain. This is different than my notes. Okay. Oh, I see. All right. So they're meant to give approximations for all numerical values. If you were to ask what values does the series match the function for, you would see that the polynomial can fit sine for all values. Same with cosine, same with e. However, 1 over 1 minus x, we talked about this a little, has an asymptote at 1. And we're not going to be able to match that function very well around the asymptote. And actually, you'll find if you were to graph both the series and the function in your calculator, the only place that you can actually match is between -1 and 1. Now that idea of where can it match is the idea of interval of convergence. I might have overreached a little here in that the interval of convergence doesn't come to 145, but in past experience you didn't get enough practice because it came so late. So I'm trying to get on it early. I apologize, this is going to be rough because I am asking you to play with this before you've actually been given a lesson on it. But it goes something like this. You're going to use the ratio test, and then there's also this idea about the endpoints, which we're not going to touch on. Let's just get started with the big idea, which is you can use the ratio test to figure out what values of x will make this converge and what won't. All right? So say we do this for sine. Now, sine is given by this series. That's the Maclaurin series for sine. Yeah? Now, when you try and figure out the x's that'll make this converge, you set up a ratio test, and it's going to be weird because you're going to see both x's and n's in it. It goes something like this. The ratio test looks like this. And for this function then, that would look something like, I'm going to blow off the -1 because of the absolute value. And it would be x to the 2 times n plus 1 plus 1 over 2 n plus 1 plus 1 factorial over x to the 2n plus 1 over 2n plus 1 factorial. Hope I have enough room here. I wrote small on paper. Now when you take this and you break it into pieces and reciprocals, then you get x to the 2n plus 3 over, now that's 2n plus 3 factorial down below, but that's the same as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. That's the top fraction. Now the bottom fraction here, when I take the reciprocal, it's 2n plus 1 factorial and x to the 2n plus 1. Now if I do a little there, now I need to figure out the x's. X to the 2n plus 3 over x to the 2n plus 1. By the rule for subtraction of exponents, if I take the top minus the bottom exponent, then that amounts to x squared over 2n plus 3, 2n plus 2. Okay? Now the limit of that. As n gets infinitely large, the bottom gets bigger and bigger, and therefore this goes to 0 times whatever x squared is, yeah? So find the limit, and the limit will have an x in it. Now in terms of when this will converge, this will be true for all x's. It wouldn't matter if x is negative, big, positive, big. If it's a finite number, 0 times any finite number is 0, and therefore it's going to be less than 1. So this is true for all. We're not talking in indeterminate form as x goes to infinity. We're saying for any actual number for x that converges. So we would say, if we would ask for the interval of convergence, all x's converge. Now, if you try that for cosine, try that on your own and see how it goes. And you should get pretty much the same thing. You'll get a limit of 0 times x squared, which is less than 1 for all x. And so, same deal. The interval of convergence is negative infinity to infinity. Try e to the x using the ratio test. Oops. Use the ratio test on the general term formula for a Maclaurin series for E. Simplify. And hopefully you'll get that the limit is 0 times x, not x squared here, but 0 times x. That's less than 1 for all x. Now the one that comes out differently is 1 over 1 minus x. The Maclaurin for that is the really clean, simple x to the n. Now the ratio test for this, the limit's even easier, and it looks something like x to the n plus 1 over x to the n. The limit of that, x. Now, as n goes to infinity, this one's kind of crazy because there's no n left in it, but it's basically like if something else went to infinity, if x has nothing to do with it, the limit is just x, for the absolute value of x. Now, if this converges when x is less than 1, then it must be the case that this converges for all x's between negative 1 and 1, and only then. Anything that's bigger, actually think about it. Would this converge if x is 2? Well, that's a series that looks like this. That definitely diverges. It fails the divergence there. So you'd see, or you could also say that this is geometric with an r that's not less than or equal to 1. And so you can see for a lot of reasons why this would only converge in a certain limited region. All right, last but not least. Again, hopefully part A and B were decent and fair, but C, that interval of convergence idea might have been an overreach on my part. Just do your best and learn. That's all I ask. And that's your job. Okay, so here we go. The 6th degree Taylor here is the first thing I would do is say, all right, 6th degree Taylor about 2. Oops, sorry. The x goes here, dumb. It looks something like f of 2 plus f prime of 2, x minus 2 to the first over 1 factorial, and continuing that until I get to the 6th degree derivative at 2, or 6th derivative and 6th power. Right? Now, using what they tell me about the function, they tell me that f of 2 is 7. When n is odd, the derivatives are 0, and when n is even, we have this rule going on for the derivatives. All right. So I'm going to blow off the first degree and go to the second. F double at 2 needs to be found. F fourth degree, fourth derivative needs to be found. And the sixth derivative needs to be found. Now, using the rule they talk about here, for the second derivative, it's 2 minus 1 factorial over 3 squared. So I'm going to go with 1 over 3 squared, x minus 2 squared over 2 factorial. For the fourth derivative, I'm looking at 4 minus 1 factorial over 3 to the fourth. So that's 3 factorial over 3 to the fourth, x minus 2 to the fourth over 4 factorial. And I could probably clean those up. I'll talk about that in a second. And then this guy is something like 5 factorial, 3 to the fifth, x minus 2 to the sixth over 6 factorial. Now that's full credit there. I did everything they asked for, and the fact that I didn't simplify, that's not a problem. It is, however, a problem if I'm looking for patterns. I would like to have a little simplified version if I wanted to write patterns. So let's think about this. If I clean this up, then isn't this something like x minus 2 squared over 3 squared 2 factorial? And this one, x minus 2 to the fourth, and these, that's when I get 3 to the fourth times 4 factorial. And then these cancel, and I get something like x minus 2 to the sixth over 3 to the fifth, 3 to the, this should be 3 to the sixth, shouldn't it? Sorry. 3 to the sixth. That's what I get for trying to do stuff without showing work. Over, these aren't factorials. Golly, I'm sorry. 3 squared times 2. 3 to the fourth times 4. 3 to the sixth times 6. So that's my 6th degree simplified. Now with that, I think I can see the pattern that they're going to ask for in B. Generally, what's the coefficient of x minus 2 to the 2n? Well, the coefficient looks something like 1 over, and if the exponent is 2n, then first and foremost, there's a 2n floating. Likewise, this has a 3 to the 2n with it, and so I feel like my coefficient would always be 1 over 3 to the 2n times 2n. And I think I answered the question, yeah. And then last but not least, the hardest part, the interval of convergence. So you cannot do the ratio test until you know what is the general term. So the general term, we kind of just touched on it here. The general term is x minus 2 to the 2n over 2n times 3 to the 2n. Okay? That's a rule for any term. So the ratio test then would look something like this. X minus 2 to the 2 n plus 1 over 2 n plus 1 times 3 to the 2 times n plus 1 over x minus 2 to the 2n over 2n 3 to the 2n. You follow? This works sideways. The limit as n goes to infinity of, so this is x minus 2 to the 2n plus 2, which I'm going to call it to the 2n times x minus 2 to the 2. That's the same as 2n plus 2. Down here I have 2n plus 2, and this I'm going to call 3 to the 2n and 3 to the 2. 3 to the 2n plus 2 can be separated by laws of exponents. Likewise, the denominator here, with its reciprocal, is 2n. 3 to the 2n over x minus 2 to the 2n. Let's do a little bit of cleanup. These, these, and let's take a step here. So I'm going to now work down. So I have x minus 2 squared in the top. And as far as these guys, putting them together, 2n over 2n plus 2. And then I have a 9 down there as well. Do I have everything taken care of? Okay, all four things are still there. As n gets infinitely large, this one amounts to 2 trillion over 2 trillion and 2. That and bigger, and so that approaches 1. And so this limit then goes to x minus 2 squared over 9. That's less than 1. Now if x minus 2 squared over 9 is less than 1, then x minus 2 squared must be less than 9. Now if you think about a world of squares less than 9, I think you'll agree that it has to be less than 3, but it also has to stop at negative 3, because negative 5 squared or negative 10 squared would not be less than 9, it would be greater than 9. So x minus 2 squared less than 9 implies x minus 2 has to be between 3 and negative 3. And so if I then move the 2 over, then I get negative 1 and 5, and that is the body of the interval of convergence. Now later on we'll talk about checking the endpoints. The ratio test actually fails when the limit is 1, so you actually have to put negative 1 and 5 in and do those separately, which you probably see on the AP key. But for now, if you got that far, got that onto your paper and followed with me, then you're good to go. Okay? That's it. That's my walkthrough on this key. I hope you're doing well. I'll also post a PDF to this if you want to just look at my answers. All right? Have a great day.